Introduction and welcome everybody. So my path to STEM, or at least to my career, was, I guess if I had to use one word, I would say non-linear. As you'll see, I did everything not the normal way, but somehow ended up somewhere. My interest, though, in STEM started when I was very young. My father was an electrical engineer. Actually, he's an electrochemist, or was. And his father was an electrical engineer. His father came over from Lithuania and didn't speak any English, and somehow managed to get a degree in electrical engineering, and then he ended up working for General Electric. And one of the things he did was to work on the elevator for the Empire State Building. So that was kind of interesting. Now, my father worked at the Edison Museum, or sorry, not the museum, the Edison Laboratories. This is a picture of the Edison Museum, which was just around the corner. And so when my father worked there, Thomas Edison had already died, but his son owned the lab. And he did a lot of interesting stuff, mostly having to do with batteries. And I used to love to go visit him, and he used to bring home chemicals and things for me to play with. Anyway, here's a picture. I also used to love to visit this museum. You can see all the machines are driven by one motor, and so they get their power from those pulleys from the ceiling. Anyway, it's a fascinating place if you can ever go there. It's in West Orange, New Jersey. Now, also my father was a musician. He played the mandolin, and his father, the elevator guy, he also played the mandolin. So I have both of those two backgrounds. So I was into model railroads and putting things together and erector sets and things like that. I also got into ham radio when I was about 12 years old. And this is not my antenna when I was 12. This is my antenna now. So actually, I lost interest in it for a while, and then got interested again, and put that up on my roof. So I've always had this interest in the technical. But then, around age of 15, I just got more and more into music, and was playing. I played violin when I was young. Then I started playing electric guitar. My mother said that I should take guitar lessons because it would make me popular. And I said, well, I don't want to be popular, and I hate the guitar. But I did it anyway, and I became popular. So for at least a little while. Anyway, so I played a lot of instruments in high school. That's pretty much all I did. I played harmonica, violin, mandolin, banjo, electric bass, jug, all kinds of things. And I played in jazz bands, bluegrass bands, folk bands, rock bands. And that took a lot of my time, I have to say. I wasn't really excelling in school that much. And then after high school, I played in a band for a couple of years touring around. But after a while, I wanted to go to college, and I was going to go to college for music. So I went to Ithaca College School of Music, and studied violin there. But I started learning about electronic music also. They had some electronic music. Then I transferred to another college, Bennington, and there they had, well, here's me playing bluegrass music before I went to college, after not sleeping all night. And the guy next to me is a very famous bluegrass musician named Vassar Clemens. We used to play festivals. Anyway, here's the Moog synthesizer at Bennington. So this is an analog synthesizer. It's all oscillators, filters, envelope generators, things like that. And the way you program it, you don't really program it, but there's patch cords, and all those holes, you connect cables from one to another, and that's how you create your piece. And I thought it was fascinating. I loved it. Then you would record it on magnetic tape. The problem is, the next day you would come in there, and there was no way you could recreate what you had done the previous day, because it all depended on the exact position of all the knobs, and even if you very carefully documented everything you did, you couldn't repeat it. So the teacher there, his name was Joel Chatterby, brought in a device that was brand new. It was called the Synclavier. It was a computer running, if I remember right, it was being controlled by a PDP-11 computer. And so I wrote my first computer program, and I was hooked. I just thought, this is the way to do it. It's repeatable. You can tell it what to do, and it's going to do it exactly the way you say. You can talk to it in a way such that if you wanted to play 15 notes, you don't have to do 15 things. You can write a short program, and then it'll play the 15 notes. So after I graduated and was trying to figure out what to do next, I applied to graduate school in music and ended up going to Stanford. Now, the reason I went to Stanford was because I thought there's 3 reasons I could go to graduate school. One would be if they have a great orchestra and they would play my music. So there's big music schools like the University of Michigan. Another possibility would be because there was a particular teacher that I wanted to study with. But as it turns out, at Bennington College, I met a teacher named Henry Brandt who became my mentor, basically, and friend for life. So I already knew what I wanted to do. It was a little bit unusual for a composer at that age, but he somehow convinced me that what I should really do is look at all this different kinds of music I was playing and integrate that into my classical music. Before that, I was trying to look at other people in Europe and what they were doing and imitate them. So I already knew pretty much what I wanted to do. So the third possible reason I thought of to go to graduate school was for a facility. And at Stanford, at this time, there was only a few places you could do music with computers. There was MIT, there was Stanford, and there was UC San Diego. And so I visited, I didn't visit MIT, but I did visit UC San Diego, and I visited Stanford. And what I liked about Stanford at the time was that it didn't seem like a school. It seemed more like just a creative lab where people were doing all kinds of things. And in fact, the music group was part of the artificial intelligence lab. And at that time, they were down on a Rastradero Road in a building that is now a horse farm that was donated to Stanford, big round building. And it was all kinds of things going on there. This is a picture of it. So over there in the upper left is the computer. It was a PDP-10. That computer, of course, is much weaker than whatever you have on your phone now. But it was shared by about 30 or 40 people at once using computer monitors around the building. And there was all kinds of experiments in computer vision, robotics, cryptography was just being developed for the first time there. There was a lot of work in desktop publishing. That was all very new. There was the first Xerox graphics printer was there. Editing with a display terminal was a new thing. It was just everything that we take for granted now was being developed there. So anyway, in this picture, you can see in the lower left-hand corner, that's a robot. It's got a camera on the top, and you can't really see, but it had 2 big wheels, sort of like a wheelchair. And it would slowly move around and navigate obstacles. So the rest of this picture, you can see that triangle thing is an obstacle. And so they would set these things up, and the robot would try to navigate. So this is like the first autonomous car. And they would put it out in the parking lot and would move around. And it was just really exciting. And so I arrived in the summer of 1979, and the teacher there, the music teacher, there was no classes then because it was summer. So he just gave me a big stack of manuals, and he said, "Here, read these." So I did, and just fell in love with it, and was having dreams about programming computers, and I just did that very intensively for a few years. Then at some point, one of my colleagues suggested to me that I might get a job where he's working. And I said, "Really? I don't really know that much." But anyway, I went and worked at a company called Intelligenetics, This is while I was still doing my degree. And they did computer programs for genetic analysis, and that was the first company that did that. So my job was to program a little device that, because they had just gotten gene sequencing working, so there would be a film, and you'd have a little pen, and you had to like press the, A, C, G, T, whatever. So that was my first job. And I also met a lot of people there that became really good friends. There's a guy named Julius Smith who was a electrical engineering PhD major, and he was trying to model violins on the computer. And around that time I was playing string quartets, and I happened to talk to the violist, and it turned out he was I think he was a VLSI major, and he had discovered this interesting way of making plucked strings. Now at the time we had been doing everything with frequency modulation synthesis. So frequency modulation synthesis, of course FM was known for a long time from radio. So in FM radio you have an oscillator that's your carrier frequency, and then you modulate the frequency of that with a voice signal. But the carrier frequency only moves a little bit. So it creates sidebands, but the whole bandwidth of the signal is still fairly small, and you can transmit it through radio. And then on the other end, it's demodulated by what they call mixing, which is really multiplying by the carrier again, gets the thing down to baseband, and then you can get the voice signal back. Well, John Chowning at Stanford figured out that you could do the same thing at audio frequencies. So you have an audio frequency as a carrier, and then if you modulate it with another audio frequency, then you can get sidebands, and those sidebands are like harmonics if those two are harmonically related, like integer relationship. So, for example, if they were both the same frequency, then you would get 1, 2, 3, 4, etc. as harmonics. But by increasing the amplitude of the modulating signal, they could get, because normally in FM you only want a couple of sidebands, but in FM radio. But in audio you actually want all those sidebands, so you want to have a broad spectrum. So that's how they were doing everything, and they got a lot of interesting sounds, and it was also very efficient. So at those, with these slow computers of the day, suddenly they were able to make complex sounds without that much computation. But the hard part was figuring out the right parameters. So this guy that I met, his name was Alex Strong, he and another colleague named Kevin Carbless, these are all graduate students, discovered this really interesting way of doing something that sounded like a plucked string. They weren't even trying to do a plucked string. I believe they were actually trying to solve differential equations. But differential equations are very closely related to music. So anyway, it turns out that if you can model a string by just a simple delay line. So if you put an impulse into a string, it's like plucking the string, and then it travels down the delay line, just like it physically travels down the string, reflects at the end of the string, comes back, and it keeps going back and forth forever. And the pitch will be the length of the delay line. But of course, in the real world, nothing goes on forever, so there's some loss. So by putting a little filter, like a low-pass filter, then you cause the string to decay away, and because it's a low-pass filter, the high energy would decay faster than the low energy. So anyway, this is a long story to say that I got into this concept of modeling the physics of instruments, and by doing that, you see how the instrument, you don't only get something that sounds like the instrument, you get something that acts like the instrument. So instead of having to figure out exactly what happens when you slide from one note to another, you just slide, and the model automatically does the right thing. So this was a great revelation to me, and I did a bunch of music with it. And when we get to the second half of the presentation, I'm going to play you a little bit of it. Anyway, so then Julius Smith got a job and suggested to these people that they hire me. Well, this was after I had graduated, a couple of years. And here's the place, and here's the guy. And here's the company. It was called Next. So this was Steve Jobs' company after he left Apple, before he went back to Apple, after he had a big fight with them. And so I was the 32nd employee. I was interviewed by Steve himself. He came in, he said, so you want to do something great? I said, yeah. He said, you want to do some killer apps? I said, yeah. He said, great, goodbye. That was my whole interview. And now there's also times later on when he would come in and scream at me, but I won't go into those detail about those. But the idea of this was the first computer that had a DSP chip that was that enabled really general purpose sound synthesis on a personal computer. So, whereas before, like I said, I had 3 choices, MIT and Stanford, et cetera. Here, now everybody could do it if you could get one of these computers. And they tried to make them not too expensive. They were still somewhat expensive, but they sold a lot of them to academia. That was their first market. So we tried to bring this physical modeling work that we've been doing, and also FM and other synthesis techniques, to the personal computer. The other thing that I personally tried to do was to combine the academic computer music with the commercial computer music. So at that time, commercial computer music meant MIDI keyboard. The Yamaha had a synthesizer called the DX7, and it could do a lot, but it was still very constrained and had limitations. And it was real time, of course, you could play it. Whereas in academia, most of the computers were not real time, but were completely general, and you could do whatever you wanted. So we were trying to combine these two goals, and so I made a software package called the Music Kit at that time. So then what happened to me? Okay, so then I got laid off. Okay, one day I came in and they said, things weren't going so well, and sorry, you don't have a job anymore. And that was pretty hard. I was really upset. In fact, I was crying. Not there, but when I got home. But the reason I was crying, believe it or not, was not that I didn't have a job. It was because I couldn't finish my project that I was working on. Because we were about to get a release out, and I just couldn't believe after 9 months of working that I couldn't release this thing. It was really disappointing. But it turns out I had a temporary job teaching that spring in Princeton, so I went there, so I had something to do. Then I came back and I was hired by the Stanford Office of Technology Licensing because this FM patent that I was telling you about, well, I didn't say there was a patent, but this FM synthesis, Stanford had a patent. They licensed it to Yamaha, they made a lot of money, but it was running out. So they wanted to have another one of those things, right? So they tried to leverage this physical modeling synthesis that Julius, in particular, had developed, Julius Smith. And there was a team of a few people, including me, and we all tried to get more patents around this thing and license them to Yamaha and other people. So I worked on that for a few years, and while I was doing that, I also met somebody who turned out to be a housemate of Julius's, and he started a company that was kind of like Guitar Hero, only 10 years earlier. They made a guitar-like thing, and they made a pick that was just an accelerometer. It was about this big. It was very cheap to make. You plugged it into your PC, and you could play a tennis racket, and you could play rhythm, and there was a game that goes with it. So I got hired by them to do game sounds, basically, music game sounds, and guitar sounds, and things like that. And then, anyway, eventually this Stanford thing, they decided they didn't want to fund it anymore, but they spun it off into a startup. So I became a founder of a startup with 6 other people, including Julius and a couple other people. And we were trying to make a better physical modeling synthesizer, a better general MIDI synthesizer using physical modeling. But turns out the computers weren't really up to it at that time still. But the people who really liked what we were doing was the game people. So we ended up doing physical models of car engines and airplanes and things like that. And they liked it because it was controllable and it would behave just like the real car or the real airplane, etc. So then that company got bought by Analog Devices, which, if you know, is a big the biggest company I've ever worked for. They're based in Massachusetts, but they had an office out here. And they called us the Audio Rendering Technology Group, and we were doing game sounds for a while. Then we ended up moving over to car audio. So I learned all about encryption, and because they were really worried about people stealing the soundtracks of the movies and stealing the movies and all that. So, but anyway, we developed a way of doing flexible sound for cars, etc. Okay, then one day I got a phone call from my boss, who is actually also the co-founder of my company, and he said, "Are you sitting down?" I said, "Yeah." He said, they just fired our entire group." Okay. So I didn't have a job again. This was 2006. So then I decided, oh, okay, I'll look around. So I looked around for like 6 months. I interviewed everywhere. But I also really kind of knew where I wanted to go, because before I had gotten fired, we had this company called Universal Audio that came to visit, and they were interested in, what they did is plugins for digital audio workstations that emulated classical studio gear and audio studio gear and things like that. And they had a processor that kind of reached the end of its life, and they were trying to replace it with the next thing. So they wanted to use Analog Devices Shark DSPs. So since I had worked a lot on that, I thought, okay, well that makes sense. So anyway, I ended up going there, and I've been working there for 10 years. So that's kind of the story of my career path. But in parallel to all this, I kept doing music. And all these jobs I had, I tried to do music with whatever I was developing. And I've tried to keep a music career going, which is a little bit of a juggling act, but I did the best I could. Most of my income comes from my day job, but I also get a little bit from my music. And anyway, my title at Universal Audio is Senior Scientist / Engineer. Now, I made that up myself because I don't really like the distinction between science and engineering, because I think that basically these days especially, everybody does everything. So anyway, I didn't want to be called just an engineer or just a scientist, so they said, fine, call yourself whatever you want. So as you can see, I've got these kind of two halves of myself, the music half and the technical half. And I didn't mention this, but I basically taught myself to program computers. I took one computer class, but it wasn't for credit at Stanford, just because I wanted to learn something. And I did take math classes when I was at Bennington College, but not that advanced. I took calculus, took real analysis, and the reason that's all I took is because I was actually scared, because in high school I didn't really, like I said, I didn't really excel that much, and so I was behind everybody. So anyway, but finally I got up the nerve to take it, and I was doing well. So then, but it was all, basically, like when you take math like that, it's all theoretical. Like they don't care what something converges to, they just care if it converges or not. Okay, then when I got to Stanford, it was the opposite. Like everybody was into like actual practical stuff, like digital signal processing, and then, they really did care whether it, exactly where it ended up. So I took some DSP classes, and so I did take some classes there in STEM, but not computer programming. But anyway, so I just kind of got good at it, I guess. I think it's partly one of those things that if you do a lot of it, you get good at it, assuming that you have at least some aptitude for it. So I've got those two halves of myself, and in my music, I also like combining things that are distinct. And like I'll take elements from one musical style and combine them with another musical style, and you create something that, like this thing, it might seem kind of peculiar, like it's got the head of a lion and the tail of a dragon or something, but when you hear it, it's like, wow, that's something I never heard before. You might not, you may or may not like it, but I try to do things I like, but they're unusual, and here's an example. So I'm kind of segueing into the research part here. So I thought to myself, what would it be like to take a recording of a bird and sort of transplant the brain of the bird into a human singer, and then have a human sing like a bird. And I love birds. That was another thing I did a lot when I was in college, was bird watching, and I would go out and try to identify all the birds by their sounds. So this is a winter wren. It's not a very good recording, but it's the recording I started with. It was on a LP, vinyl LP. The winter wren has the longest song of any North American songbird. Let's see if this works. Okay, so that's a long twittery thing. So I sent it through a bunch of processes. The first thing I did was to run it through a program that extracted the pitch and the amplitude, just those two things. And the way that worked was, it has a small window of time, it takes a Fourier transform, it looks for the peak in the spectrum, and because the bird is so high, it's basically just one peak. This program would look for more peaks, but I only set it to look for one peak, so that would give me the main frequency. Then it would step along. It would also measure the amplitude of the peak, so the frequency and the amplitude, step along in time, measure it again, measure it again. So then the output of this thing would be a function of time, two functions of time, one for frequency and one for amplitude. So then the next thing I did was I augmented the time. In other words, I slowed it way down. The next thing, so that became, instead of that long, it became a much longer thing. Then I wrote a program that would segment it. So it would look for flat places in the pitch, and I would say, okay, those are notes. And I would segment that. Also, if the amplitude went low, I would say that's a note. So I tried to figure out where the notes were, so to speak. Then I wrote another program that would tune it, because this was a piece, actually it was a commission for a piece for chorus and computer voices. So I wanted the computer voices to sing in tune with the chorus. So I had to tune these things to the pitches that people sing, because obviously the bird doesn't care about the equal tempered system. So then I worked the range, so it starts kind of small and it gets bigger and bigger. This was just for a dramatic effect, so that the solo would kind of go somewhere. And finally, probably the most interesting thing of all was I mapped the frequency axis to a set of vowels. So when the bird, or the human bird, is low, let's say the lowest vowel is oo, and then it would go e and then ah, let's just say. So then if the function went then the voice would go riau. And when there's trills, it would go ya 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 ya, like that. So you get all kinds of diphthongs, and kind of funny. You'll hear it's kind of funny. And I like music that has some sort of humor to it or satire, and I think you'll probably think that it's somewhat funny. Now, let's see. Why didn't the slide advance? Let me try that again. There it goes. Now this is just the computer part. I'm not playing you the chorus part, because I just want you to hear the computer. Now, another thing was that the program I was using at the time to do the vocal synthesis was based on a technique developed in Paris. And what they did is they would record, they had like a model of the human vocal tract, more or less, and they would take little impulse responses and trigger them over and over, which is basically similar to what happens with your glottis. Your glottis vibrates, it's creating little pulses, and then your throat and your mouth and your nose are like a filter. So it's by having the impulse response of the vocal tract and then triggering it periodically, you get vocal synthesis. And this was great for vowels, but it wasn't very good for consonants. So I just made a piece that was just vowels. So here it goes. Okay. Now, the rest of the piece was a little bit more melodic and harmonic. Unfortunately, I don't have a recording of the rest of the piece, but because I only have a little bit of time. But you can kind of imagine that this was sort of sailing over a chorus singing. Now, that took 1 month of computer time to compute. In those days, if it took a month, you didn't really have very much time to do it over and over. So you kind of had to get it right, as right as you could the first time. When we were able to do things in more real time, or either closer to real time or real time, then you could refine things a lot more, and so it was a challenge in those days. Oops, that's it again. Sorry, what did I do? Oops, I hit the wrong button. Just a second. Sorry. Okay, here we go. So I also asked myself, when I was composing for instruments, I would always try to write something that fit with the instrument I was writing for. So if I was writing a flute piece, I'm not going to write the same kind of music as when I'm writing for guitar. So I would try to learn as much as I could about the way the instrument worked and write music that fit with the instrument. But with computers, what do? The computer is just a general purpose computing machine. It doesn't really have anything idiomatic. And by the way, just in case, I don't know, you probably have different backgrounds, but when I say computer music, it could mean a few things, but one of the main things I mean, or especially at this time, was that you have a digital to analog converter, and you have a bunch of numbers, and it's just playing those numbers. So you basically have the waveform, and it's sampled in time, and you're turning it into a voltage and sending it to a loudspeaker or several loudspeakers. So when you have that, you have to generate those numbers somehow. So how do you do it? It's like you could do it any way you wanted, and there's nothing that's particularly idiomatic. So that's why discovering this physical model idea was such a great thing for me, because now I had something that I could work with. Like, oh, I've got a model of a string, so that's like something I understand, and I know how they work. But now I can abstract it and extend it in all different directions. So let's see what this is. Oh yeah, so here's an example of a beginning of a piece I wrote using this plucked string. And it starts with just a single note. And if you listen really carefully, you'll hear that there's like up and down picking, there's picking close to the bridge, picking farther away from the bridge. There's, what else? I can't remember. Anyway, you'll hear it when you'll understand it when you listen. Now, I want to emphasize this is not sampled. This is not a recording. This is completely generated from mathematics. Steve Jobs used to like to say, generated from pure mathematics. Well, it's not really pure mathematics, but okay. So here it is. This is the beginning of a piece I wrote called Silicon Valley Breakdown. We only have one of the two channels, unfortunately, so that's why it didn't sound like I expected. I wonder if I can quickly figure out why that is. Let me try playing it again, and I'll mess around with the volume controls. You know, at the end there, what you're hearing is the open strings of the instrument. Imagine if you had a piano and you had a mallet, like a timpani mallet or something, or a bass drum, and you're hitting inside the piano. So you're resonating the strings that way. Anyway, you get the idea. I'm not sure about the balance, but you could hear that there was a lot of variation in just a single note by changing all these parameters. And they were parameters that were based on the physics. Okay, so that's just trying to imitate a guitar more or less, or a mandolin maybe. But then I thought, well, what would it be like to create a really fat string like the cables of the Golden Gate Bridge? So I tried to do that. I did it by duplicating the string, having a whole bunch of them right next to each other in pitch, increasing the stiffness, because a Golden Gate Bridge cable is going to be pretty stiff. And that increases the inharmonicity. So instead of the harmonics being exact integer relationships, they'll be stretched. So it sounded like this. This starts very high and then goes down. Okay, now I look at the clock and I see that I'm supposed to be moving on to the next phase. So I'm going to play a couple of things, a couple more things, and then call it a day. This is another area of combining two contrasting elements. In this case, I was combining two different instruments. So I started getting interested in real-time performance, and I was working with a device called the radio drum, which is, it was actually invented at Bell Labs to be a three-dimensional mouse. There's two mallets or sticks, and it knows where they are in space. And these are actually two radio transmitters, and it's like a pizza box size thing is a receiver. There's 4 receivers in the 4 corners, and it can figure out where it is in space more or less. And so I started thinking, well, okay, you can play it like a percussion instrument on the surface, but wouldn't it be interesting to map the language like that a percussionist plays? Like when you play drums, you learn the whole language of techniques, right? And then when you play piano, you learn a completely different language. So I thought it would be interesting to map the language of percussion onto a piano. So this is what that looked like. Kind of an old video, but you'll get the idea. get the idea. Anyway, this is the car engines that I was mentioning very quickly. I hope. Piece for saxophones and car engines. This is a guy I worked with named Trimpen. He's a mechanical genius artist up in Seattle, and he made all these chimes for me. I inherited them when my teacher that I was telling you about died. He left me all these chimes, and I asked Trimpen to turn them into robots. So those things coming off from the side are electromagnets. And when I send it a MIDI command, they hit the chime. And I ended up doing a piece again with my friend Andy, who was just playing the radio drum with these chimes. And I'm going to show a little bit of this, and then I think I have to move on to... Okay, I'm going to jump ahead here. So this is a piece... This was a piece for string players all around the audience, and the chimes were hung from the ceiling over the audience. There was 2 robot xylophones, a robot piano, and a robot glockenspiel. So you get the idea there. Well, I'm supposed to give you some advice. It's hard for me to give you advice because like I said, I didn't really do anything the right way exactly. But you know, what I would say is that, you know, there's so much talk now about like, oh, it's so competitive in the job market and all that. Well, I think the most important thing is to cooperate with the people around you and like look at who's next to you, and there's, you know, these are the people that you're making contact with that you could like do projects with or start a company, or maybe they'll get a job and they'll like recommend you or something. So as you can tell, that helped me a lot. Like every job basically came from a different one. Even if I got fired, then somebody I knew there would recommend me. And so that's one thing. Another thing is it helps to be lucky, because unfortunately, you know, people say like when they're successful, they say it's all because of me. It's because, you know, and when they're failing, they say it's all bad luck. But actually, there's a lot of luck in succeeding as well as failing. So I don't know how you automatically get some good luck. I've had some good luck. I could have had more good luck, and not gotten fired. What else? Like I said, like, you know, everything I did was something that I really wanted to do. Like I was really driven by my own interests, whether it was music or technical stuff or computer music or whatever. It's a lot easier to work when you're really loving what you're doing. So, you know, I know there's a lot of practical pressure to do something that, you know, you think will be the most likely to be able to get you a job, but it's also, if people see that you're really like excited about what you're doing, then they respond to that also. So, you know, make sure you have fun. And that's my advice. Okay, now I guess it's question time. No questions? If there's no questions, I'll have more time to play stuff. Oh yeah, go ahead. What did you say?
What's your favorite comedy period?
Oh, my favorite piece? Well, it's usually the most recent piece. You know, whatever I've written most recently. The piece that they're doing at the by the Redwood Symphony that he mentioned before on April 7th. That's. Yes. Any other questions? Yeah. It's not too hard to make your own plugin because you can easily get like a VST plugin. You can get a wrapper and you download it, compile it, and it'll just, you know, it'll be an example. Then the question is, well, what's it going to do? That's the hard part, is coming up with an algorithm that's interesting. But you know, you could do anything you want. People have done a lot of things that I thought would be the exact thing they wouldn't want to do, like bit crunching. That was like the opposite of what we tried to do, where you throw away bits and you make it, you know. So, you know, people just use your imagination, I guess, and experiment. The nice thing is you can do it, you can hear it right away, put in some controls. It's pretty hard to model like the circuit stuff. I've done a few plugins at Universal Audio. I did a model of the first digital reverb, but I was lucky enough to have the guy who actually did it send me his like sketches and his block diagrams. And even then, it was some tricky stuff to get the right number of bits here and there and everything. Other questions or comments or complaints? No? Come on.
Do you have an album out?
Yeah, if you go on iTunes, or go to my website, it's jaffe.com, there'll be links to albums. Mostly they're online now, iTunes or things like that. But yeah, I've done a few solo ones, and I've been on like a whole bunch. I was actually, like, way back in 1983, one of the first CDs that was ever made was called The Digital Domain. And it was to show off like CDs, like, 'cause nobody knew what CDs were. And so I had a piece on that, but that's not available anymore. Yeah? Okay, cool. Yeah. Anything else? Yeah?
You mentioned, like, when you were at university in 1979, you mentioned sort of like being around for a lot of like kind of like big advances in signal processing. Do you still see those kinds of advances even now, or is it kind of like a lot of the techniques you're using nowadays have sort of already been discovered and you're focused more on using them then?
No, I think there's still a lot of discoveries going on. The problem is that I did a lot of the work I talked about, I did in universities, but now I've been in industry. Now, the bad thing about being in industry is you can't talk about what you're doing. So, like, there's a lot of great stuff happening at Universal Audio that I can't talk about. but you know, things like the way they model circuits and the way they analyze them is pretty advanced, and has advanced since I've been there. And I'm doing some new cool projects, but I can't talk about them. But it's true that, like I think you know, you're sort of onto something. It's like 20 years ago or 30 years ago or whatever, you could kind of come up with something sort of obvious, and nobody would have thought of it before. Now there's like people all over the world that have already like combed over this stuff. It's sort of like, you know, mathematics. Like to find a really new branch of mathematics is pretty hard. It's possible, but it's not easy because so many brilliant people have already thought of, you know, have been there before. Whereas computer music is still relatively new, computer audio, but it's getting older. So, yeah. Other things? Questions? Okay, well, I guess we'll wrap it up. Thanks.
Wait, don't wait to do that.
No good is going to come from it.
Oh my god, but you can try.
Yeah, but you can simulate it.
Yeah.